Hi, so today we're going to be talking about our modeling complex systems final project, where we modeled floodplain restoration scenarios using cellular automata and heterogeneous mean field models. So why do floodplains matter? So in the Lake Champlain Basin of Vermont, there's a total maximum daily load to limit the amount of phosphorus reaching Lake Champlain that's been in place since 2012. And in response to this TMDL, funding and implementation of nature-based solutions such as floodplain restoration has been intensifying in the Lake Champlain Basin. And many rivers have been disconnected from their floodplains due to agricultural or housing or other development. And this causes multiple issues because floodplains have water quality benefits by slowing down floodwaters and allowing for sedimentation of particulate materials that carry nutrients that pollute the lake. And also they help to slow down flood wave velocity. And you can see, so they have benefits both in terms of water quality, which is an example of poor water quality is on your right, and water quantity, an example of an extreme flood is on your left in Montpelier, Vermont in July 2023. And just a quick river geomorphology 101, because it will come into play in our modeling setup. We modeled different river types, ranging from a steep gradient river. So these rivers are often disconnected from their floodplains and have more capacity to transport sediment than they have access to sediment to transport, to a low gradient meandering river, slow moving river that has more access to sediment than it has power to actually transport that sediment and is generally well connected to its floodplains. So our modeling approach, we first used a cellular automata model and then fed the outputs of that model into our heterogeneous mean field model. And we modeled two different restoration strategies and their impact on watershed phosphorus transport reduction. The first strategy was a single large-scale downstream floodplain restoration, and the second strategy was distributed smaller-scale upstream floodplain restorations. And these restoration strategies were modeled on three different river types, as we mentioned before: low gradient, meandering, mid gradient with some bends, and steep gradient rivers, and across two different scales, small versus large watersheds.
Okay, so starting off with our first modeling strategy, we used a CA model to model the dynamics of phosphorus flowing down a river, or over our three river types. So starting off with some of the high-level assumptions that we made when we built that model. First, we assumed that the flow direction of P is always going to be down the river, so there's no P going back up the river at any time steps. We assumed open boundaries, so P is going to enter the river at the top of the river and exit the river at the bottom. We used 2D modified von Neumann neighborhood, primarily just to decrease computational complexity. We used three cell states: P, water, and land. And finally, we assume that P enters the river stochastically with a constant probability and can be absorbed by the river banks also with a constant probability. Okay, so going through the rule book that we used for our CA, we used a set of 5 rules in a hierarchical structure shown here, moving from left to right. At every time step, there is a probability that any P cell is absorbed by the riverbank. And if that doesn't take place, then we have a set of rules determining how the cell will move down the river, either down or left to right. And we highly biased our cell movement so that P was more likely to flow down the river than to the left or the right. And finally, if a P cell can't move because it is boxed in by land and other P cells, etc., it can just remain in place. Okay, so going through 3 simulations we ran here with our 3 different river structures. You can see on the left, we have our meandering river with many bends. We have, in the middle, we have our river with few bends, or medium grade river. And then on the right, we have our steep river with basically no bends. And pretty much right away, you can see that there's a large buildup of P around all of the bends in the rivers that have bends, whereas the long straight river allows P to just flow directly down. So you can see that the P is being slowed down by the bends that we have in our rivers. Okay, so we ran our 3 CA river structures for 2,000 time steps each and recorded the amount of P that flowed out of the rivers. And you can see that the 2 rivers with bends performed very similarly. They both allowed a little bit less than 40% of the P that entered the river out of the river into the lake or the next place the water is going. Whereas the steep river allowed closer to 60% of the P that entered the river out of the river.
Great. So after the cellular automata model, we use those absorption rates based on the different river types as inputs into our heterogeneous mean field models and how we model the different river types. So we assumed that the mass of phosphorus was directly proportional to the stream order. And an example of stream order can be seen with these numbered nodes. So it's essentially a sum of the 2 nodes that come together to create, or the 2 edges that come together to create a node. And we assumed a constant removal rate of phosphorus by floodplain restorations of 0.3. And we also assumed a constant transmission rate, which was that transmission rate as determined by the cellular automata model. So we modeled the 3 different river types by adjusting their transmission rates. And we modeled 2 different watershed sizes by instantiating the model with different number of nodes in the first layer, 40 to 50 for a small watershed, 160 to 170 for a large watershed. And then we randomly generated the next layer by adding in a random number of first order streams and continued this process until our final node, we had a final terminal single node. And then we tested both restoration strategies. So 1 large floodplain restoration at the downstream node of the network, the terminal node, or 10 distributed floodplain restorations throughout the network on all 6 permutations of river type and watershed size. And here are some of the results of our different model runs. So on the left, this is a single versus distributed restoration strategy, phosphorus reductions in a low gradient river in a large watershed. And you can see that the single large floodplain restoration significantly outperforms the distributed floodplain restorations in terms of phosphorus reduction. But in a steep gradient river, that's flipped. So the distributed floodplain restorations actually outperform the single large downstream floodplain restoration. And then this is the same figures, but on a smaller watershed. And you can see that the large floodplain restoration outperforms distributed floodplain restorations, no matter the river type, in a smaller watershed.
So here we see a more fleshed out floodplain visualization. It's a simplified model versus the previous model to better visualize floodplain behavior. Here we see a 4-level inverted perfect binary tree, which is also represented through a directed graph. The regular floodplains are gray nodes, and the restored floodplains are sky blue nodes. There are 5 restored floodplains, which are stochastically chosen. The phosphorus is evenly distributed across the leaves, which are located at the top, and it percolates down for each level. Here we see a color bar, and this is the phosphorus reduction level, and it's showed by the edges of the graph. So the lines, the directed lines that are connected from the top nodes to the bottom nodes. As for the dynamics, it's node-based phosphorus reduction. Once the phosphorus edge encounters a restored floodplain, again the sky blue, we see a reduction level equals 1 minus alpha to the power of the level. It's applied, and the edges reflect, the color of the edges reflect this, where alpha is the predefined constant, and the phosphorus reduction factor, and the level is the depth of the binary tree, where the top is 0. The restored floodplains act as like a stronger filter per each level, and the regular non-floodplain nodes do not modify edge values.
some of the main takeaways from our modeling. So in terms of the effectiveness of floodplain strategies, we found that in pretty much all scenarios, the single downstream floodplain restoration outperformed the distributed strategies for phosphorus reduction, except for large watersheds with steep gradient rivers. We found distributed floodplains did outperform a single downstream restoration strategy in that scenario. And then in terms of watershed size, we found that for small watersheds, distributed floodplains were less effective versus a single downstream restoration strategy. And this kind of makes sense because in a larger watershed, you're going to have more higher order upstream nodes. So if you're randomly distributing floodplains throughout your network, you're more likely to target a high order node and have that reduction propagate through the system, and that probability is lower in a smaller watershed. And in terms of our model assumptions, we essentially assumed that our system was at steady state and that phosphorus essentially just scaled with the drainage area or the stream order of our nodes. And while this does kind of negate the impact of land use on water quality or more additional effects of floodplain restoration, such as the slowing of floodwaters, allowing more time for sediment bound nutrients to settle out of the water column. This steady state assumption is often used in water treatment technology models. And these additional parameters could be incorporated if a finer resolution was needed. But we do feel that this model is effective as a broad stroke first pass when designing a restoration strategy for a given watershed. And some of those more involved modifications could be applied depending on the watershed that's being modeled and its characteristics, and also the resolution of management guidance that is desired by the people utilizing the models. So those are our main takeaways. So thanks for listening.